All right, today we're going to be looking at filling in a note page where we're going to start kind of look more idea at polynomials with something called synthetic division. Definition of synthetic division is written on the page. It says a procedure, so it's a method, a process, to divide a polynomial by a binomial. So again, talking about those math words, so to take something that's many terms, dividing it by something that's two terms, using coefficients of the dividend and the value of r in the divisor x minus r. So in class today we asked about what comes to mind when we hear synthetic, and someone said kind of fake, and it's kind of maybe just that. It's kind of like a shortcut for long division or dividing kind of through that traditional long division process. That's more of a shortcut, more kind of a fake way, a simpler way to kind of get through some of this division with polynomials. So let's kind of look at an example in how this process of synthetic division is going to work. We're going to be taking synthetic division and trying to use the polynomial 2x cubed minus 5x squared plus 5x minus 2 and dividing it by x minus 1. So taking a polynomial, dividing by a binomial, and even more specifically, dividing by a linear binomial. Synthetic division will only work if I'm dividing by a linear factor, a single degree of x. So we're going to be starting in standard form, starting from high to low, and making a list of all the coefficients from our highest degree down to our constant. So I have 3, 2, 1 constant. So if I look at my coefficients, we're going to take a 2, we're going to take a negative 5, a positive 5, and a negative 2. And I'm going to kind of draw this big L. If I was missing a degree, missing a placeholder in descending order, then I'd have to fill in a 0. So if we kind of want to make some notes here, these are all the coefficients in standard form, so from high to low. So in standard form, and I would need to include a 0 for any missing terms. So let's say I didn't have this piece. I just had 2x cubed plus 5x minus 2. I would have to put a 0 in the x squared spot to hold its place. Now on the outside, if this is my divisor, x minus r, I'm going to be taking that r, and that's what's going to go on the outside of my synthetic division process. Basically, I'm going to be taking the 0 as if this was a factor, or I'm going to be taking the opposite side of the divisor, if that probably helps us the most. So if it's an x minus 1, I'm going to be putting a positive 1 over here on the outside. So this is going to be the opposite side of the divisor. And here's kind of how the process of synthetic division is going to work. Very first thing I'm going to do is take that leading coefficient and I'm going to drop it down. So I'm going to drop down by 2, so where I'm going to start. Then I'm going to multiply, so 2 times 1. So this direction here I'm going to be multiplying. 2 times 1, I'm going to write that down. Then I'm going to take these two and add them together. So negative 5 plus 2 is going to give me a negative 3. And I'm going to repeat that process over and over again. So multiply negative 3 times 1, negative 3, write it down, add my column, 5 plus negative 3 will give me a positive 2. So again, 2 times 1 multiply, write that down, add my columns, I get a 0. This last number here will always be our remainder. And notice there my original polynomial started with an x cubed. I only use the coefficient, but I really have an x cubed here. And if I take an x cubed polynomial and divide it by a linear binomial, a linear divisor, a single x, then if I reduce this degree by x, I'm now down to an x squared. So my quotient will always be reduced by 1 degree. So what I have left here are the coefficients of the quotient, and it will always be 1 degree lower. So if I kind of come down here to this kind of summation here, if I take 2x cubed minus 5x squared plus 5x minus 2 and divide it by x minus 1, what am I left with? My remaining quotient is 2x squared minus 3x plus 2. No remainder left over. So let's kind of just take a quick glance, not part of the official note page, but what if I had to kind of include that 0 for the missing term? So let's just kind of make one up on the fly here. What if I had 4x to the 4th plus 3x cubed minus x plus 7, and I want to divide it by x plus 3. Again, totally made that up. If I'm going to do synthetic division, which is possible because I'm dividing by just a linear divisor, I'm going to take all my coefficients in descending order. So I have a power of 4, a power of 3. Oops, I'm missing that power of x squareds. So in theory, I really have 0 x squareds in that spot. Minus x plus 7. So if I go to list my coefficients, we have a 4, a 3, a 0 for the x squareds, negative 1, and 7. My x to the 4th, my x cubes, my x squareds, my x's, and my constant. Everything has to be accounted for from the highest degree on down. Since I'm dividing by x plus 3 on the outside here, it's going to go the opposite side of my divisor. So I'm going to take a negative 3. And here we go with the process. I'm going to drop down 4, multiply negative 12, add negative 9. Probably shouldn't have made these numbers so big. Negative 9 times negative 3, positive 27, add 27. Multiply 27 times 3, what's that, 60 and 7, 81, so minus 81, add negative 82. Multiply, I'm going to get a positive, that's a 246. And then add, we're looking at a 253. This last number right here is my remainder. I started with an x to the 4th, divided by a linear factor, so I've reduced my quotient by 1 degree, so I'm now at an x cubed. So my answer would actually be 4x cubed minus 9x squared plus 27x minus 82 with this remainder. Here I didn't have one, so it divided perfectly evenly into that. Here I have a little bit left over, or maybe even a lot left over. So I'm attaching my remainder as 253 over what I still have to divide by, x plus 3. The process. So using this process to analyze other things with polynomials as the unit goes on. So back at the note page. 2 other theorems associated with polynomials, the factor theorem and the remainder theorem. Factor theorem says the binomial x minus a, so that linear divisor, is a factor of the polynomial if and only if, basically I get a remainder of 0. So when I take 8 and I divide it by 4, no remainder. So we say 4 is a factor of 8. But if I take 8 and divide it by 5, I have something left over. I have that remainder. So 5 is not a factor of 8. Same theory, same idea, works for binomials. If it divides perfectly, wonderfully, evenly into the polynomial and I get a remainder of 0, then yes, that's a factor. If it doesn't, if I have something left over, then that divisor is not a factor of the polynomial. So let's test it and see. I want to show that. I want to do some little proof that x plus 5 is a factor of x cubed plus 2x squared minus 13x plus 10. Then I want to see if I can use that and find all my factors to this cubic polynomial. So let's start. I look for my highest degree. I have 3, I have 2, I have 1, I have constant, so no zeros are needed this time. My coefficients are 1, 2, negative 13, and 10. If I want to show that x plus 5 is a factor, I'm going to be going the opposite. So I'm going to put a negative 5 on the outside of my process. Here we go. Drop down 1, multiply negative 5, add negative 3. Multiply 15, add positive 2. multiply negative 10, add and get 0. So since we got a remainder of 0, so since my remainder equals 0, what does that tell us? Yes, x plus 5 is a factor. And if x plus 5 is a factor, again, I started with an x cubed, which means I've divided and reduced my quotient by 1 degree, so I'm now at an x squared. So my current factors look like the x plus 5 that we started with, that found out that worked, and then our remaining quotient. So we have x squared minus 3x plus 2. This depressed polynomial, kind of once we've gone through the synthetic division and reduced this by 1 degree, they call this remaining quotient our depressed polynomial. So x squared minus 3x plus 2 can be factored more. Because it's a quadratic, we have knowledge of how to factor quadratics on our own without the help of division. Is there anything that multiplies to be positive 2, adds to be negative 3? Yes, there is. It factors to x minus 2 and x minus 1. So if we look at the full factorization, the simplest factorization of this polynomial through synthetic division, we discovered the factor of x plus 5. Through our own quadratic knowledge, we could finish with x minus 2, x minus 1. Complete factors. Next theorem up here, the remainder theorem. Again, this is fancy math talk. It says the remainder when you divide f of x by x of a is the constant f of a. Basically saying once I divide, whatever my remainder is would be the value of the function evaluated at that x value, at that point. So this next example says if my polynomial is 3x to the 4th, etc., find f of negative 2. Earlier in the year, we would have taken negative 2 and we would have plugged it in everywhere we saw in x. Now we're going to test it using the remainder theorem. So here we started with x to the 4th. 4, 3, 2, 1 constant. No zeros needed. So 3, 2, negative 5, 1, negative 2. This time I'm evaluating f of negative 2, so I get to take the outside as is. I'm going to put the negative 2 out here. This is not a factor, this is the actual point of evaluation. So I'm not having to do the opposite here. I get to take negative 2 as is on the outside. Process stays the same. Drop down 3, multiply negative 6, add negative 4. Multiply 8, add 3. Multiply negative 6, add negative 5. Multiply positive 10, add 8. Here's my remainder. It is not 0. So x plus 2 is not a factor, not divide evenly into this polynomial. So what does that tell us? Because we got a remainder of 8 from the remainder theorem, we know that f of negative 2 has to equal 8. That the point negative 2, 8 would be on the graph. But because it's not a factor, that's not an x-intercept, and doesn't divide evenly into the polynomial. And so let's just check. Let me kind of just verify again what this means. If I would put negative into the function, meaning 3 times negative 2 to the 4th plus 2 times negative 2 cubed minus 5 times negative 2 squared plus negative 2 minus 2. Negative 2 to the 4th is a positive 16, so 16 times 3, there's a 48. Negative 2 cubed is a negative 8 times 2, so I have a minus 16. Negative 2 squared is 4 times negative 5, so minus 20. Minus 2 minus 2. So what are we looking at here? A 32 minus 20? Minus 2 minus 2? What's that, a 12 minus 2 minus 2? a 10 minus 2, and there we see that 8. Maybe, because you can't see it. So me putting in negative 2 and evaluating shows me that that remainder theorem kind of does the exact same thing. So not always getting an even remainder of 0, but if I do, it tells me that that factor, that divisor, is an actual divide evenly perfect factor of the polynomial. If it doesn't help me so much with the factorization, but it does still give me some details. It still gives me a point on the graph, and it gives me a function value at a certain point.